Hello everyone, welcome to Tech-Lavya. Please like, share and subscribe.
Today we are starting May 2018 question paper, and in today's lecture we are going to discuss part 1 of that solution. So let us see what is the question. Now again, first question will have 6 subsections, and out of those 6 subsections you have to attempt any 5. So each question comprises of 4 marks. Okay, so let us see what is the first A question. What is the difference between ideal source and actual source? Illustrate the concept. Okay, fine. So basically, let us talk about ideal source and practical source. Now if we talk about a voltage source, the voltage source is represented by this or this, and a voltage source is said to be an ideal voltage source if the internal resistance of that voltage source is 0. Please remember this, okay? This is in case of voltage source, okay? A voltage source is ideal if its internal resistance is 0. However, we know that anything cannot be ideal. So, if it is a practical source, it means what? Or an actual source, it means what? It has some amount of resistance. So this is how we represent a practical voltage source, which has a voltage V and it has some internal resistance. It can also be represented by RS, which is called source resistance. Okay, we have to remember that the internal resistance or the source resistance of a voltage source is very low. Fine, okay. So basically what I am trying to say is that, if it has a very low internal resistance, then it almost approaches the ideal source, right? Another point is an ideal voltage source is ideal when this voltage provided by this voltage source is always constant. The voltage provided by that voltage source is always constant. Constant with respect to what? So, irrespective of change in the current. Fine? Okay, so understood? So, this was about voltage source. Now, if you want to explain this with respect to current source, then current source will be exactly opposite. Okay, so current source is represented by, suppose this, then its internal resistance would be infinite. An ideal voltage source has internal resistance to be equal to infinity. However, if you consider it to be actual source, then you have to consider its internal resistance, which is very high, and it is assumed to be connected in parallel. Okay, again, if we talk about current source, then I would say that the output current has to be constant. Okay, no matter any parameter changes, my output current has to be constant always. Fine. So if I wish to draw the characteristics, suppose this is V, okay, it has to be constant. This can be I or x-axis can be t. but it has to be constant. So if it is like this, I would say the source is constant. But if it is practical source or actual source, then it may slightly change. So this dashed one will give you practical source or actual source. Fine. So I hope this is clear now. Now let us go to the next question. In a balanced three-phase circuit, the power factor is 0.866. What is the ratio of two wattmeter readings? Okay. So basically here power factor is given, which is 0.866. Now how do we represent power factor? It is cos phi. So what we will get, the value of phi we can get from cos inverse 0.866. So what happens to phi? It becomes 30 degree. Correct? Now in 2 wattmeter reading, we have an equation which is tan phi is equal to root 3 times the difference in the wattmeter reading upon the sum of the wattmeter reading. So what we will do is, we will first calculate what is tan phi. So tan phi will be tan 30, correct? And tan 30 is 0.577. Okay? So this ratio becomes 0.577. So W1 minus W2 upon W1 plus W2 will be 0.577 upon root 3, correct? So upon root 3 will be 1.73. So this ratio comes out to be 0.33. So I will cross multiply this and I will get 0.33 W1 plus W2 equal to W1 plus W2. So when I solve this, I will be getting 0.33 W2 plus W2. I am taking W2 on one side and W1 on the other side. Okay, so this comes out to be 1.998. So the answer is W1 by W2 is 1.998. This is the ratio. Can be approximately equal to 2. The next question is calculate RAB. Okay. Now please pay attention here that this resistance and this resistance is shorted. Correct? So let us see how it looks like. So this is RAB. Then we have 40. This is 30, 40. This is 15. Now if we talk about the 60 and 30, they are in parallel because they are shorted at the other end also. So it will be 30 into 60 upon 30 plus 60. So this becomes equal to 20 ohms. So here we have a resistor of 20 ohms, right? So this is my connection. So what is this combination? Series combination 60 ohms. Correct? Now if you see this 15 and 30, they are in parallel. So what is the combination of 15 in parallel with 30? It is 15 into 30 upon 15 plus 30. So that is 450 upon 45. That makes it 10 ohms. So what is the next equivalent circuit? This. So this was 60 ohms and this was 10 ohms. This is A, this is B. Now see, these two resistances are not in parallel because here we have open in between. Correct? It means that 60 and 10, they are in series. Okay? So this RAB is actually 60 and 10 in series, which makes it 70 ohms. So the resistance between terminal A and B will be 70 ohms. So this is the answer. Fine. Let us go to the next question. Now derive the equation for resonance frequency for a parallel circuit in which capacitor is connected in parallel with a coil having resistance R and inductive reactance. So basically it is this kind of circuit. And they are asking the resonance frequency. Now this resonance frequency for parallel circuit has already been done in our regular lectures. Okay, so you can refer to that lecture. It is parallel resonance topic. It is under the topic of parallel resonance. Fine. Next is, what are the classification of DC motor? Specify applications of each one. Okay. Now again, DC motor in the new syllabus, in the earlier syllabus it was a regular syllabus content, but then in new syllabus it comes under the self-study section. Fine. So this particular topic was covered in self-study section under the topic of DC motor. In self-study section we have DC motor and DC generator. Okay, so you can refer to that lecture. Last question is, derive the equation of single phase transformer. Again the same question has been covered in chapter 4 single phase transformer, and we have derived the equation also. So you can refer to that lecture for this answer. So with this we are stopping today's lecture. We shall be meeting with more questions in the coming lectures. Thank you.